Assalamu alaikum warahmatullahi wabarakatuh. Our lesson today is going to be organic 2 under subtopic alkenes. Our previous lesson was on alkenes, but today we are going to check on alkenes. So alkenes are also hydrocarbons, made of carbon and hydrogen. The difference between alkenes and alkanes is that alkanes have double bond between carbon atoms, therefore are said to be unsaturated, while alkanes have single bond between carbon atoms, therefore alkanes are said to be saturated. So alkenes are said to be saturated hydrocarbons. So we say are saturated hydrocarbons. Hydrocarbons with double bond between carbon atom. So the functional unit is where we have the double bond. That forms the functional unit in alkenes. And they have got a general molecular formula of unsaturated. Sorry, this one is supposed to be unsaturated. Are unsaturated hydrocarbons with double bond between carbon atoms. So we say alkenes are unsaturated. So the unsaturation is due to the presence of the double bond between carbon atoms. This makes alkenes to be unsaturated. They have a general molecular formula of CnH2n, where N represents the number of carbon atoms. N here is representing the number of carbon atoms. So let's have a look at naming of alkenes. How do we name alkenes? So naming alkenes. Naming of alkenes. Naming of alkenes also depends on the number of carbon atoms, just like alkanes. So we have the prefix, which depends on the number of carbon atoms, and we have the suffix ene is being added to the prefix. And we have already said that the prefix is determined by the number of carbon atoms. And the first member of alkene is ethene. We have ethene as the first member of an alkene. So we have the number of carbon atoms here. We have molecular formulae, name, and molecular formulae. Molecular formula. So we have 2 carbon atoms. That's the first member. That gives us the name is ethene with the molecular formula of C2H4. We have 3 carbon atoms, that is propene, with the molecular formula of C3H6. And we have 4 carbon atom, that is butene, with C4H8. C4H8. But when it comes from butene, when naming from butene, we are supposed to identify the position of the double bond. The position of the double bond needs to be identified. For example, if we talk of butene, 1, 2, 3, 4, and we place the double bond there. So we have this one here. This is hydrogen, 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 hydrogen. So this one is supposed to be named as but1N. but, one in. That is from butene. The position of double bond needs to be identified. We have pentene, we have hexene, we have octene, we have nonene, and decene. So, what I want us to check is isomerism in alkenes. Isomerism in alkenes. And isomerism we said is the existence of compounds with same molecular formulae but different structural formulae. Existence of compounds with same molecular formulae but different structural formulae. So alkenes being unsaturated, they undergo or they show two types of isomerism. One is the branching isomerism. The second one is positional isomerism. So let me first start by positional isomerism. So we say that alkenes shows both branching and positional isomerism. So let me first start by the positional isomerism.
B1 and B1.
Positional isomerism. Positional isomerism is referred to as the shifting. This is just the shifting of the position of the double bond across the structure. So it's the shifting is the shifting of the position of double bonding across the structure. So it is the shifting of the position of the double bond across the structure. So we call that one as positional isomerism. For example, let's have a look at butene. Positional isomerism in butene. So we have butene with C4H8. We have the first carbon atom 2, 3, 4. Make the double bond to be on carbon number 1. Then we have these ones as hydrogens. Those are hydrogens. Now when it comes to naming of this, the position of the double bond should be given the lowest number possible. Therefore, if we start naming from this end, this is 1, 2, 3, 4. 1, 2, 3, 4. So the double bond is nearer from this end, whereby it is going to be given position 1. When we start from this side, the double bond will be on position 3. Therefore, we name it as butane, but it will be but1 in, butene, but1 in, showing that the position of the double bond is found on carbon number 1. If I shift the position of the double bond and place it in here, I'm going to obtain 1, 2, 3, 4. Shift the position of the double bond there. Then we have this one as hydrogen, 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 hydrogen. This is named as but2in, but2in, whereby this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. 1, 2, 3, 4. So you can see in this one, whether we start naming the carbon atoms from this end, the double bond is going to be found on carbon number 2. And if we begin from this end, it is still going to be on carbon number 2. But if we shift the position of the double bond and place it here, now we have 1, 2, 3, 4. We place the double bond there. Then we have those ones as hydrogen. We have these ones here, hydrogen, hydrogen, that is hydrogen, 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 hydrogen. There is going to be no difference between this structure and this structure here. Because, so we are going to find that this structure here and this one here have the same names, whereby the position of the double bond, now we are going to start naming it from this end, since the double bond is nearer from this end. Therefore, this one is still going to be but 1N. So you can see that when dealing with the positional isomerism, we are only shifting the position of the double bond. And this forms the easiest isomerism that we can have, the isomers, only changing the position of the double bond. Then we check on branching isomerism. Branching isomerism. Branching isomerism. So we said under branching isomerism, this is where the substituent group alkyls are being formed, is where the substituent group into bracket alkyls are formed. Alkyls are formed. So we have a methyl, we have ethyl, we have propyl, we have butyl. Depending on the number of carbon atoms, then the substituent group can also be formed. Therefore, let's still have a look at branching isomerism in butene. Butene. So we have butene still, which is C4H8. We have the first isomer is the straight one with a double bond there. That is hydrogen, 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 hydrogen. So this one is named as but 1N. Now I want to form a substituent group, which is a methyl. In the formation of the methyl, methyl is CH3. So we are going to carry the whole of this one here to form a methyl. And now we have our straight chain having that one there. We put now the methyl at that position. Then we have that as hydrogen, 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 hydrogen. Now this one here forms a methyl. That forms a methyl. The methyl is found on carbon number 2. And the position of the double bond is on carbon number 1. Even if we bring it on this side, there will still be no changing on the name. So it will be 2-methyl propene. 2-methyl propene. 2-methyl propene. So we have this one as the substituent group, and this gives us the branching isomerism in alkenes. Branching isomerism in alkenes. Now the next part under alkenes is we check on how can we be able to prepare alkenes in the lab. Lab preparation of alkenes. Lab preparation of alkenes. So when it comes to lab preparation of alkenes are prepared in the lab through dehydration of alkanols. We dehydrate alkanols using concentrated sulfuric 6 acid as a dehydrating agent, or we use aluminum oxide. Apart from that, another condition that should be observed during dehydration is the temperature. This reaction needs to occur between a temperature of 160 to 180 degrees Celsius. Temperature below 160, maybe 140, we have partial dehydration. Therefore, instead of formation of alkanols, we obtain alkanals, which means there is going to be incomplete dehydration. Therefore, we say that alkenes are prepared by dehydration of alkanols. Alkanols using concentrated sulfuric 6 acid or concentrated sulfuric 6 acid or aluminum oxide. So the condition needed is concentrated sulfuric 6 acid, which acts as a dehydrating agent. Aluminium oxide acts as a dehydrating agent. At the same time, it acts as a catalyst. So we have said that the reaction occurs at a temperature of 160 to 180 degrees Celsius. 180 to 160 degrees Celsius. Below that temperature, there is going to be incomplete dehydration. Therefore, instead of formation of an alkene, we get alkanals. And the corresponding alkene will be obtained from its corresponding alkanal. For example, if I want to obtain ethene, I dehydrate ethanol. If I need propene, I carry out dehydration of propanol. If I need butene, I carry out dehydration of butanol. So, example of the reaction. So preparation of ethene. Preparation of ethene. Ethene is prepared by dehydration of ethanol. So is prepared by dehydration of ethanol. So we have ethanol, which is C2H5OH. This one here is liquid. We have H2SO4 liquid at a temperature of 180. That is 180 degrees Celsius. We are going to get C2H4 gas plus H2O liquid. So we have already obtained ethene. This is ethene. This one is here is ethanol. So we have said that apart from concentrated sulfuric 6 acid being used as a dehydrating agent, we can also use aluminium oxide. So which means we have C2H5OH liquid. We use Al2O3 solid and a temperature of 180 degrees Celsius, giving us C2H4 gas plus H2O liquid. So that's the product that's going to be obtained. We have already prepared ethene. Ethene is an organic substance that is a hydrocarbon which is non-polar. Therefore, it is insoluble in water, and that makes us to collect it by over water method. We collect it by over water method. If you look at molecular mass of ethene, that is 12 times 224 plus 4, giving us 28 as the molecular mass. So you find that ethene cannot be collected by use of downward delivery or upward delivery. This is because its density is almost equal to that one of air. It has a density almost equal to that one of air. Therefore, we cannot collect it by upward delivery or downward delivery. The most efficient method in collecting this gas is by use of over water method, since it is insoluble in water. Or we can also collect it by use of syringe. Now let's have a look at some of the physical properties of alkenes in general. Physical properties of alkenes. Under the physical properties of alkenes, one physical property of alkene is solubility. Alkenes are insoluble in polar solvent, which is water. They do not dissolve in water, but soluble in organic solvent, which are non-polar. So we say here are insoluble in polar solvent, into bracket water, but soluble in organic solvents. Soluble in organic solvent. Now, how does the solubility compares? The solubility is decreasing as the molecular mass increases. So we say their solubility decreases with increase in molecular mass. Molecular mass. So as the molecular mass increases, their solubility is also what? Increasing. Then the next one, we check on melting and boiling point. Melting point and boiling point. What determines the melting and the boiling points of molecular substances is their molecular mass, or the type of the intermolecular forces of attraction which exist between the molecules. Alkenes have weak van der Waals forces that makes them to have low melting and boiling point. But how does the melting and boiling points compares in alkenes? Their melting and boiling points increases as molecular mass increases. This results to increase in the strength of intermolecular forces of attraction. So we say they have low melting point and boiling point due to weak intermolecular forces of attraction. But their melting point and boiling point increases with increase in molecular mass. So as the molecular mass increases, the strength of the intermolecular forces of attraction also increases, making their melting and boiling points to increase. That tells us if we have ethene and we have pentene, pentene will have high melting and boiling point than ethene. This is because it has bigger molecular mass with strong intermolecular forces of attraction. And the third property is, the third physical property is maybe the density. And they said that density is determined by the molecular mass. As molecular mass increases, the density also increases. Therefore, the density in alkenes will also increase as the molecular mass increases. Then the next part, subtopic under alkenes, is on chemical properties. What are some of the chemical properties of alkenes? And we said that when we talk about chemical properties is how alkenes reacts with other chemicals or with other substances. So we check on chemical properties of alkenes. Chemical properties of alkenes. So the first chemical property of alkene is combustion. We check on combustion. Combustion means burning in air. Burning in air. How does alkenes burns in air? So the first one is we check on chemical properties of alkenes. And the first one we have said combustion, that is burning in air. Alkenes which are saturated burns in air with a blue and less sooty flame. They were saturated. That is alkenes. Now, what about alkenes? Alkenes, we say that they are unsaturated. This is due to the presence of the double bond. So due to their unsaturation, alkenes burns in air with a yellow sooty flame. They burn in air producing a yellow sooty flame. So we say alkenes burns in air producing a yellow sooty flame. They burn in air producing a yellow sooty flame, forming water and carbon 4 oxide, that is if it is complete combustion. And in complete combustion, they produce carbon 2 oxide and water, which is steam. So yellow sooty flame forming water and carbon 4 oxide. Carbon 4 oxide. So let's have a look at burning of ethane, that is C2H4 gas plus oxygen gas. This gives us CO2 gas plus H2O liquid. Balancing of the chemical equation, we put 2 here and we put 2 here. So that is 4 plus 2, we put here 3. So 3 moles of oxygen reacting with 1 mole of ethene, producing 2 moles of carbon 4 oxide and 2 moles of steam or water if it is cold at room temperature. So we are going to get that. So this will be the product formed under complete combustion. So which means here we are having excess carbon 4 oxide, excess oxygen. Under limited supply of oxygen, instead of forming carbon 4 oxide, we obtain carbon 2 oxide. We obtain carbon 2 oxide. Therefore, that is the first chemical property. The second chemical property is addition reactions. Alkenes were saturated, therefore they were undergoing substitution reaction. Alkenes, being unsaturated, they undergo addition reaction. Addition means to add something. So we are going to add other molecules across the double bond. We are opening up the double bond to add more molecules to make them saturated. So we talk of addition reaction. Addition reaction of alkenes. Addition reaction of alkenes. The first addition reaction is hydrogenation. Hydrogenation. Hydrogenation is from the word hydrogen. Therefore, this is addition of hydrogen molecule across the double bond. So we say this is addition. This is addition of hydrogen. Hydrogen across the double bond. So we are adding hydrogen across the double bond. We are going to convert alkenes to alkanes. What is the condition necessary for the process of hydrogenation? So condition necessary for this reaction, condition for hydrogenation are: 1, we must have a nickel catalyst. A nickel catalyst. Apart from the nickel catalyst, we can also use what we call palladium catalyst. Then the second condition is a temperature of 180 to 250 degrees Celsius. So the range of temperature for the process of hydrogenation must lie between 180 to 250, which means if you carry out that reaction at a temperature of 200, still convenient, 180 or 190, that temperature is still convenient for the process of hydrogenation to occur. And we have said that we also need to have a catalyst, and the catalyst used is the nickel catalyst. Apart from the nickel, we also use palladium as the catalyst. So if you have an alkene, we have here alkene plus hydrogen, alkene plus hydrogen in the presence of the nickel catalyst or a temperature of 100 degrees Celsius, we are going to get an alkane. So alkene is converted to alkane. Then let's have a look at a simple reaction, that is reaction of ethene with hydrogen. How does ethene react with hydrogen? Reaction of ethene with hydrogen. So having ethene, which is bond, hydrogen, we are reacting it with hydrogen molecule. This one is also a gas. Here we have nickel catalyst, a temperature of 180 degrees Celsius. We are going to get this one here, that is hydrogen, 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 hydrogen. So this one is ethene converted to ethane. If we carry out hydrogenation in propene is converted to propane. So this reaction is known as hydrogenation, addition of hydrogen. Now, where do we have industrial application of hydrogenation? In factories, we have manufacture of oils. When making cooking oils, we have that one which is in solid form, and we have that one in liquid form. Oils are said to be unsaturated. Oils are unsaturated, while fats are saturated. Therefore, the process of hydrogenation is applied in industries in converting oils to fats. Example is manufacture of margarine. We talk about the blue band. Blue band is, initially it was in liquid form. Therefore, the process of hydrogenation is being done into it and being converted into solid blue band that you can see. So we say that industrial application of hydrogenation is in converting oils to fats, e.g. manufacture of margarine. So we also have manufacture of margarine. So that gives us the industrial manufacture, industrial application of hydrogenation. So we are making oils which are unsaturated to become saturated by addition of hydrogen. Even if you go to the shop, we have the cooking oils. We have one which is in liquid form and the one which is in solid form. There is no difference. The only difference is the one which is in liquid form, they have carried out a process of hydrogenation so that they convert it into what? In solid state. But they are just the same. So which means that the one which is in solid form is also obtained from the oils which was in liquid form. So the only thing which is being done is by carrying out hydrogenation and make it saturated. Then the next B is halogenation. Halogenation. This is another addition reaction. Halogenation is from the word halogen. This is addition of halogens. Is addition of halogens to the double bond. When we talk about addition of halogens, and we have said that the process is halogenation. So, for example, if we have ethene This is ethene, hydrogen, 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 hydrogen. We are adding bromine molecule. This gives us C, C, single bonds, hydrogen, 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 bromine, bromine. We call this one as 1,2-dibromoethane. So an ethene changes to ethane because the double bond has opened up. Now we have single bond. Single bonds are characterized in alkanes, while the double bond is characterized in alkenes. So this is an ethene, and this reaction does not require sunlight like alkanes. We saw that when alkanes were reacting with hydrogens, were reacting with halogens, the condition which was necessary was the UV light or sunlight, and that was being needed to break the molecules into atoms for that reaction to occur. Now, the difference between the reaction of alkenes with halogens and alkanes with halogens is that this one does not require UV light, and the alkanes was needing a UV light for that reaction to occur. In fact, if you introduce sunlight in this reaction, the reaction becomes more faster. It becomes more faster than when you just carry it out in the absence of UV light. So here we have added bromine molecules. We get 1,2-dibromoethane. If we use chlorine, we are going to get 1,2-dichloroethane. 1,2-dichloroethane. So a similar reaction will also take place if we use iodine. Iodine will be 1,2-diiodoethane. 1,2-diiodoethane. We are only adding either chlorine molecules or bromine molecules or iodine molecules in the structure. Then we have C is the addition of hydrogen halides. Addition of hydrogen halides. Addition of hydrogen halides. When we talk of hydrogen halides are hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. That's what we mean by hydrogen halides. Therefore, when we are adding the hydrogen halides, for example, we want to add hydrogen iodide, we are going to add hydrogen atom and iodine atom into the structure. For example, if we have here ethene, that is hydrogen, 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 plus maybe hydrogen iodide. So this one is only going to add one molecule, one atom of halogens. So we get here C, C. So this is hydrogen, 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 and iodine. So how do we name this? This is named as iodoethane. Iodoethane. Iodoethane, because we have added an iodine molecule, iodine atom. If we will have added hydrogen chloride, it will be chloroethane. Chloroethane. If we add bromine, it becomes bromoethane. If it is fluorine, it becomes fluoroethane. So that gives us the product that's going to be formed when we have that reaction. And from there, we are going to conclude, but still we have more addition reactions of alkanes, which is going to be in our next lesson under alkenes. Assalamu alaikum warahmatullahi.